So I want you to try something for me, just for a second. Picture the ground beneath your feet right now.
Oh,
Just
yeah.
visualize what is actually down there. If you're like me or, really anyone who isn't a professional geophysicist,
Yeah.
you probably picture a layer cake.
Right.
A nice, neat layer of topsoil. Then maybe some clay, a clean slab of sandstone, and finally hard bedrock at the bottom. It's orderly. It's stacked. It just makes sense.
It is comforting, isn't it? The problem is that model is basically a fabrication.
Well, that's a great start to the deep dive. Everything I know is a lie.
I mean, it's a useful simplification for a textbook, sure. But if you actually look at the raw data, that whole layer cake model is just a blurry illusion. We are essentially blind to what is actually happening underground. We treat the Earth's crust like a stack of pancakes, but in reality, it's a chaotic, high-entropy mess.
And that is the terrifying reality we're unpacking today. We're doing a deep dive into a paper that claims we've been looking at the Earth all wrong.
Completely wrong.
Yeah. We're talking about a research paper titled Application of Infinite Fractal Descent, or IFD, for High-Resolution Subterranean Mapping of Fluid-Bearing Geometries. It's by Encumgelen Nesson-Jargel, and it was published just last year in 2025.
And this isn't just a paper about, a better drill or a stronger radar. This is a heavy hitter. Nesson-Jargel is arguing for a total paradigm shift in geophysics. We are moving from reflection, which is basically taking a picture and hoping for the best, to mathematical descent.
Mathematical descent. It sounds like something from a Jules Verne novel.
Yeah.
But the stakes here are very real. We're talking about finding water in the Gobi Desert where none should exist, predicting earthquakes before the ground shakes, and tracking invisible pollution plumes. And somehow, it all hinges on three things that sound like they were pulled out of a hat.
Fractals, bionic computer chips, and the golden ratio.
Right. It sounds like a disparate list of ingredients, doesn't it? Bit of a word salad?
It really does. But once you get into the mechanics, they fit together with this terrifying elegance.
So let's start with the blindness. Why are we so bad at seeing underground? We have radar, we have sonar, we have those seismic trucks that thump the ground. Why isn't that enough?
Think about how those technologies work. You bang on the ground, and you listen for the echo. Ground-penetrating radar, or GPR, and seismic reflection, they all treat the Earth as a collection of voxels. Think of them as 3D pixels.
Like Minecraft blocks.
Exactly like Minecraft. We assume that inside each little block, the density is uniform. But nature doesn't build in blocks. Nature builds in flows, in fractures, in veins. When we force the Earth into these voxels, we are applying a low-pass filter.
So we're blurring out the details because our math assumes the world is made of squares.
Right. It's like trying to map a spider web using Lego bricks. You're going to lose the delicate structure. And the Earth's crust isn't a clean stack of pancakes. It's a chaotic mess. The technical term is a high-entropy environment. It scatters signals.
So when we look for water or oil, we're basically looking through frosted glass.
Worse. We're looking through frosted glass while someone is shining a strobe light in our eyes. You get a vague shape, but you completely miss the story. You miss the connectivity.
Enter Encumgelen Nesson-Jargel and this concept of infinite fractal descent. The paper introduces something called scale relativity. Break that down for us, because that sounds like physics homework.
It's actually quite intuitive. Scale relativity asks a simple question. How long is the coastline of Britain?
I feel like this is a trick question. It's a set number, isn't it?
Is it? If you measure it with a satellite, you get one number. If you walk the beach with a yardstick, measuring around every big rock, the number gets bigger.
Oh, I see.
Yeah, and if you measure around every grain of sand with a microscope, the number becomes effectively infinite. The reality of the object depends entirely on the scale of the ruler you use.
Okay, I follow. The closer you look, the more detail you find.
And the Earth's subsurface works the exact same way. It's a continuous multi-scale system. And this brings us to the fractal part of the title.
Fractals. The trippy shapes you see on screensavers.
Yes, but in nature, they are highly functional. A fractal is a shape that is self-similar. If you zoom in, it looks the same as when you were zoomed out. Think of a river delta. It looks like a tree. Zoom in on a branch of that delta, and it looks like the veins in your lung.
Wow.
Yeah, zoom in on a microscopic rock crack, and it looks like the river delta again.
And fluids, like the water we're trying to find, follow these patterns.
That is the key insight. Ancient riverbeds, aquifers, hydrothermal channels, they branch. Nesson-Jargel points out that fluid structures have a very specific fractal signature.
The paper mentions the McGinty-Nautil scale equation. That sounds incredibly intense. What is that actually doing?
It's a mouthful, but the concept is beautiful. It suggests that the underground isn't a static thing, it's a scale-dependent wave function. Basically, the equation allows the computer to slide down the scales. It doesn't just look at the big picture, it mathematically descends through the layers of magnification.
Which brings us to Pellis entropy.
Mhm.
Now, usually when I hear entropy, I think of my apartment getting messy, things naturally get a disorder.
That's actually a perfect analogy. In this context, we are using the Pellis fractal information theory to sort matter based on how organized it is.
So rock versus water. Who wins the organization contest?
Water wins hands down. Active aquifers moving water have low entropy. They are highly organized. They follow that nested, branching, self-similar pattern we just talked about. They are flowing with a purpose, following the path of least resistance.
And the rock.
Crystalline bedrock or a pile of rubble has high entropy. It's stochastic, it's random, it's a total mess.
So we have organized water and messy rock. And the paper claims this hierarchy is scaled by the golden ratio, the 1.618 number.
It sounds almost mystical, doesn't it? But the golden ratio, or phi, shows up everywhere in nature. Pine cones, galaxies, seashells. Nasanjagal argues it also dictates how water carves paths through the Earth's crust. It's simply the most efficient way to distribute energy.
Okay, so if we know water looks like a fractal and follows the golden ratio and rock looks like random noise, we can just filter out the rock.
Precisely. This is the filter equation in the paper. And it treats noise differently than we're used to.
Usually if you have static on the radio, you just turn up the volume of the music, right? You try to overpower the noise.
That's the brute force method. IFD is much smarter. It defines noise as a lack of symmetry. Remember, the algorithm is looking at the ground at scale 1, then scale 2, then scale 3.
Descent.
Right. Now, random geological noise, that high entropy bedrock, doesn't repeat a pattern. It looks different at every scale because it's random. So when the computer integrates across the scales, the noise suffers from destructive interference. It literally cancels itself out.
It's like if you have a crowd of people all screaming random words at different pitches,
Yeah.
eventually it just becomes a wash of white noise.
Spot on. But the signal, the water, the aquifer, it repeats its geometric logic. It looks the same at scale 1 and scale 10, so it gets reinforced. It has constructive contribution.
That is incredibly clever. You don't fight the rock. You just let the rock cancel itself out because it's disorganized.
And the result is a map of fractal potential represented by the symbol psi. It effectively erases the rock and lights up the water like a neon sign.
And there's always a but. With technology like this, doing this math sounds expensive. We aren't just taking a picture. We're running a recursive algorithm on millions of data points across infinite scales.
It is computationally ruinous. The paper explicitly states that doing this on a normal computer, even a modern supercomputer, is inefficient to the point of impossibility. You need a completely new kind of hardware.
Enter the IVP, the IFD voxel processor. This thing sounds like an absolute beast.
It is, and this is where the engineering gets as wild as the math. The IDP isn't a flat chip like the one in your phone or laptop. It is a 3D stacked mesh.
So the chip itself looks like a layer cake.
Ironically, yes, but more like a complex lattice. It uses hardware-native recursion. This blew my mind. The physical layers of the chip actually correspond to the mathematical scales of the formula. Layer 1 of the chip handles the macro scale, layer 2 handles the mesoscale, and so on.
That is mind-bending. The physical shape of the computer mimics the math it's solving.
It has to. The paper mentions it's capable of processing context lengths equivalent to 2 million tokens. That is massive. It creates a physical path for the data that mirrors the fractal path of the water.
But here's my question. I know from building my own PC that when you stack electronics, heat is the enemy. If you stack chips like that, wouldn't it just melt?
Heat is a massive problem here, but not just because of melting components. You have to remember what this computer is connected to, the sensors.
Right, we'll get to the sensors in a second.
These sensors are measuring microgravity. If the chip gets hot, that heat creates thermal fluctuations. To a highly sensitive gravity sensor, heat looks like gravity.
Oh, wow. So if the computer gets hot, it creates ghosts in the data.
Exactly. It hallucinates mass that isn't there.
Yeah.
So they couldn't just slap a fan on it.
Mhm.
They used bionic design. They etched cooling channels directly into the silicon that mimic blood circulatory systems.
Fractals again.
Fractals again. They used a branch level of 5. The data shows this keeps the processor at a steady 60 degrees Celsius and is 15% more efficient than standard cooling.
I love that symmetry. They use the geometry of nature fractals to cool the computer that is searching for the geometry of nature underground.
It's symmetry all the way down.
Okay, so we have the theory with scale relativity, we have the brain with the 3D chip. Now we need the eyes and ears. How does this system actually sense the ground?
It uses two main types of sensors. First, SQUIDs.
SQUID, superconducting quantum interference devices. Best acronym in science.
It's definitely up there. These are the most sensitive magnetic and gravitational sensors we have. They measure microgravitational gradients. We are talking density changes as small as 10 to the negative 15. They can feel the difference in weight between a rock full of water and a rock that is dry.
Because the water is less dense than the rock.
Exactly. Or more dense, depending on the surrounding material. It detects the anomaly.
And the second sensor.
Piezofractal transducers. These are the ears. They listen for vibrations, but specifically, they listen for the 1/Fod noise signature. That is the specific sound of active fluid flow.
But the part that stood out to me wasn't just the sensors, it was how they placed them. I was imagining them just scattering these things across the desert. But the paper talks about a Golem ruler.
Yes, the Golem ruler. This is a deep cut from mathematics.
Explain this to me like I'm 5.
Okay, imagine a regular ruler. The distance between inch 1 and 2 is 1 inch. The distance between 2 and 3 is 1 inch. It repeats. It's redundant.
Yeah.
In a Golem ruler, every distance between any pair of marks is unique. No two distances are the same.
Why does that matter for finding water?
It maximizes spatial frequency coverage. It means that with fewer sensors, you get more unique data points about the geometry of the ground. It allows the system to reconstruct a 3D image without needing to carpet bomb the area with equipment. It's ruthlessly efficient.
So we have the sensors collecting this unique data. We have the 3D fractal chip processing it. But who is driving the car? There's an AI involved here, right?
Of course. It's called the scaling transformer. Its job is to manage the depth of the calculation.
Because you don't need to look at everything with a microscope.
Exactly. If the AI looks at a section of ground and sees pure chaos bedrock, it stops. It says nothing to see here and saves power. But if it sees a pattern, a hint of that low entropy water structure, it descends. It zooms in.
It's like a hawk hunting. It glides until it sees movement, then it dives.
That's a great visual. But there's a risk with AI. We know this. AI can hallucinate. It can see patterns that aren't there.
Right, like seeing a face in the clouds. Or seeing water where there is just sand.
Exactly. So they use something called telepit.
Telepit. Sounds like a sci-fi teleportation device.
It stands for Physics-Informed Neural ODEs. This is the safeguard. It's a constraint. The AI isn't allowed to just draw whatever it wants. It is mathematically constrained by the actual laws of fluid dynamics and gravity. It literally cannot create a map that violates the laws of physics.
That gives me a lot more confidence. And the paper mentions this reduces errors, the RMSE, by nearly 57.7%. That's a massive jump in accuracy.
It's the difference between a guess and a measurement.
So this all sounds incredible on paper. But does it work? The paper discusses a validation study.
They ran a simulation using a DLA proxy, basically a fake digital aquifer hidden inside a block of white noise, a digital needle in a digital haystack.
And then they asked the infinite fractal descent system to find it.
Yes, the result was 90% fidelity. Traditional linear echo methods failed completely. They couldn't distinguish the signal from the noise.
That is a staggering difference. But let's take this out of the lab. The paper focuses heavily on a specific real-world location, Mongolia. Specifically, the Gobi Desert.
Yeah.
Why there?
The Gobi is the perfect testing ground. It is geologically complex, and the stakes are incredibly high. First, there's water scarcity. The Gobi has paleo water.
Paleo water, old water.
Ancient water. These are deep channels that were recharged during the last glacial age. They are hidden, and they are vital for the people living there. Finding them with traditional radar is almost impossible because the Gobi is so dry and creates so much scatter. IFD is designed to find exactly these kinds of fractal branching channels.
So we are hunting for Ice Age water to keep people alive today.
No.
But it's not just about finding water to drink. It's also about pollution. This part scared me a little.
It should. The paper discusses the Erdenet tailing ponds. This is a massive mining operation. There's molybdenum and copper contamination.
And the fear is that this toxic sludge is leaking into the groundwater.
We know it's leaking. The problem is we don't know how. The hidden plumbing of the earth connects the waste sites to the rivers, like the Congal River. But because those connections are deep and fractured, we can't see them.
So IFD could basically map the sewer lines of the earth. It could show us exactly how the poison is moving.
Which is the first step to stopping it. You can't plug a leak you can't find. Enk Ambulan Sandag from the Mongolian Academy of Sciences has been studying this, and this technology acts as the missing link to map those pathways.
There was one other application that I found fascinating. Earthquake prediction.
The Gobi Altai fault. A major seismic zone.
How does finding water help predict an earthquake? I thought earthquakes were about rocks smashing together.
They are. But think about what allows that smashing to happen. Friction. Fluid-filled fissures act as fault lubricants.
Fault lubricants.
Think of a tectonic plate like a heavy crate you're trying to push across a floor. If you pour oil under it, it slides. Deep underground, high-pressure fluids reduce the friction on faults. If we can monitor the fractal health of these fluids, see how they are moving and building up pressure, we might see the slip before it happens.
So we aren't just looking for water. We are looking for the grease in the gears of the planet.
That's a powerful way to put it.
So what does this all mean for you, the listener? We've gone from high-level math about entropy to bionic cooling chips, all the way to saving water in the Mongolian desert.
If we connect this to the bigger picture, I think we are witnessing the end of the static Earth era. We are moving toward a world where we treat the planet not as a rock, but as an informational field.
A scale-dependent informational field.
Yes. We used to think the deeper we dig, the simpler it gets. Just rock. Now we realize the deeper we go, the more complex the information becomes.
It changes everything about how we mine, how we build, and how we protect our resources.
It really does. It turns geophysics into data science.
I want to leave you with a thought, something to chew on after you finish listening. We talked about how the Earth's subsurface is apparently organized by the golden ratio and fractal geometry. And we talked about how our most advanced computers, the ones finding this water, are now being built to mimic that exact same geometry.
The bionic chips, the fractal cooling.
Exactly. So are we inventing a new way to see the world? Or are we just finally building technology that speaks the same language as nature?
That is the question. Maybe we're finally just learning to listen.
Thanks for joining us on this deep dive. We'll see you next time.